right. Yeah, great to see all you guys here. It's nice to see for the long time, for the first time in a long while, a lot of the Bolt team and Broombot as well, being represented in one Zoom meetings is a pretty great opportunity, especially since our last design review was in the fall. So yeah, we're all very excited to be here and to see what you guys had to present, even though we may have had a hand in helping organize this. But anyway, I think it's best to get started with an overview of what we've been doing recently. So of course, this would not be a complete meeting without updates about Broombot. It is in fact something that is happening. There are work days that are occurring and there's excellent progress being made. And with Bolt, there's definitely a lot of key points that we'll be covering. There are some characteristics of this bot that we determined pretty early on that we really wanted to pursue. And there are a lot of technicalities such as designing walking and things of that sort that in sort of problems and engineering challenges that may arise from these sort of design choices we made. So it's really interesting. We'll have a lot to tackle next year. And I think that in general, we're gonna have a very interesting set of design choices to make in our hands.
Yeah. All right, getting right into it. Very exciting. We just have some really quick updates on Broombot. Broombot is not really in the design review phase anymore. If you tell us to change something now, we won't do it. Basically because the robot's all the way built or close to it. But we do want to update you guys just because there's some really exciting developments. The first thing is that we've had work days and they've been a blast. And I have just like a little slideshow of people working in the lab. I remember to take pictures. So just to show everyone like the progress we've been making, how fun it is to see the whole robot come together. I really like this picture, especially because it looks like they're all circled around like a cult leader. They're like trying to touch his shoulders or something. So that's been a lot of fun. And updates from the specific teams. We've got a lot of the mechanical systems in. So the drivetrain system is built. The payload system can be seen with the vending machine coils on the inside. And then it's on this drawer that slots in and out. You can see the motion there. So it can be pulled out of the robot to be refilled. And the arm, which has gone through a lot of different revisions. The arm is now working, it's motorized. There's still a couple of issues that we're working on fixing. You can see that sort of offering of the granola bar, that process is in place. On the electrical side, we made a lot of diagrams. I went back through all the files I had and I was like overwhelmed by the quantity of diagrams. So I'm like, I figured I would show some of them off. We had a lot of work to do on the electrical side of things this year because none of that had ever really been figured out. So we went in and worked, had to get all of these components, these individual components working together. And a lot of them we do have working together. We have all of our power distribution done. We have all of our different controllers talking to each other. So this is some place where we still have progress left to go, but a lot has been done. And a lot of things are functional. As you can see, we've got drive working, head turn, facial animations are complete. And there's a picture of our lovely electronics tray with all of our junk has been put into it. And on the software side, a lot of progress as well. We plugged as many things into a Raspberry Pi Zero as it's possible to plug into a Raspberry Pi Zero. And the result of that is that we can now use our Raspberry Pi and our touchscreen like a computer, which is really fun. The touchscreen, like the display, underwent a lot of changes, and they've continued working on computer vision, voice recognition, and integration, as well as the web dashboard, all getting the touchscreen together with everything. Just like a ton of work on that front. And then here's some results. This was at a recent event. We went to the Maker Faire that they hold on the Hill, and we brought Broombot, which was his debut, his first day out of the lab. Not really functioning, but being there, showing face. Met Josie Bruin, they're BFFs now. And just advertising X1 with Guardian, with our combat robots, with all of our other ASME stuff. So that's what's going on with Broombot. Hopefully one day soon it will be completed and fully functional and interactive. We're getting there. So the next event where you can see Broombot will probably be our combat robot competition, SoCal SmackDown on May 22nd. Broombot will be there making an appearance. So make sure to come to it. All right, without further ado, let us move on to progress on Boelt.
Yeah, so as you can see here, this is just a render of a pretty recent render actually of really the culmination of the work of both the chassis and the legs teams, or at least the design progress of both. The legs team also was working on some kinematics work as well. But what you may see here may be a bit obvious, but of course it is 4 legs. We have a movable spine that has one link in the center, and this is currently a 12 motor setup. Of course, we expect more motors to be in the final robot to actuate either the tail, ears, or parts of the head. But this is a great base that we have for Boelt going forward. And I'm sure everyone will be glad to explain the design process made. So
yeah, not shown in this is head and tail are a part of our goals for this robot. But we have been working on this as our base structure for the robot for this year. All right.
Hi, everyone. I'm Daniel. I'm one of the sub-team leads for the legs and kinematics team. And so this quarter, our main focus was to get the CAD kind of down for our legs so we can have like a prototype. And then one thing we encountered while we were doing this was we had to redesign part of the leg to have 3 motors instead of 2 due to some excuse me some work with the spine and the movement path of the dog's feet. And then the other thing was, again, going back to the spine, is making sure that our leg fit well with the chassis hips and spine design, which, as you can see from these images, they do quite nicely, and it looks very similar to a dog. So we're very happy about that. So one of the early design things we went through was deciding if we were going to do inverted or non-inverted legs. And so I'm going to pass it over to Gabe, and he's going to kind of talk a little bit about that.
Yeah, so with this decision, one of the main factors we considered was just designs to reference from, because we took a lot of inspiration from quadruped robots like Boston Dynamics Spot, which is the yellow one on the left. And another design efficiency thing we considered was just being able to mirror the leg. And with the inverted design, the front and the back is going to be exactly the same, and left to right is just it's reflected. And then the one benefit that we are losing out on is that the non-inverted, which is the one on the right, it has a symmetrical balance for the movement calculations. For example, going forward and backward would be exactly the same, but for ours, we would have to make an adjustment. But ultimately, overall, the inverted had more benefits, so we decided to go with that option.
Am I going? Yeah,
Yep.
okay. Yeah, so part of the design process was determining how to increase the friction between the feet and the ground because they're just balls. So there's not a whole lot of like surface area. So we wanted to cover the feet in rubber. And we were thinking of a couple ways to do that. And I had used this room temperature vulcanizing rubber stuff in high school, and essentially just make a mold for it and put whatever you want to have the rubber like coating it in the mold, and pour the like a liquid in, and it hardens into a rubber. And I found in high school, at least, there was really it stuck well, and it didn't like come off, it didn't move around a lot, and I thought that could really work for what we're trying to do with Boelt. This picture is the exact stuff that we used. I found that the material link is there if you want to read up on it also. And I know Tap Plastics is a pretty good place to get stuff from. I think just the most difficult part of it will be creating a mold for the ball of the foot, because you have to hold the ball like exactly where you want it so it doesn't like get offset. But I think if you make it like a really exact an exact mold, it'll work pretty well.
So if you recall from our previous design review, we were originally going to use steppers for all of the 12 motors, or I guess before it was 8, but steppers instead of servos because we already had them in the lab, and so they'd save a lot on budget because we didn't have to buy anything. But when we looked into it more, we realized that there's some disadvantages that steppers have that servos don't. In general, servos, they're a lot pricier, but they with that price comes like a general performance advantage. They also, because they come with a lot of modules that provide functions such as like closed loop feedback. So that's the image to the right there, where it compares. So basically what it does is it compares how much the motor should have moved with how much it actually moved, and uses that to adjust for like how much more power or less power it should put in. And this is useful for like fluctuating loads. So when the robot's moving and the legs hit the ground, that creates a different load that shifts as the leg moves around. And since I think the point of Boelt is ultimately to focus on realistic movement, it'd make a lot more sense for us to use servos over steppers. It's also that servos tend to be a lot smaller, or not a lot smaller, but it's smaller by a significant amount than steppers. So we decided that they'd be a lot better for our project overall.
And just to go a little bit into the material choice in terms of design. So we decided on 3D printing using PLA. There was a few factors that went into this, but basically it's strong enough for our applications while being lightweight, cheap, and then most importantly, we get the main benefit of rapid prototyping, which is that we can create complex geometries without weird machining processes. So also we get the benefit of multiple iterations. We can make little tweaks and test, which is a lot easier than if we were using something like aluminum and we had to keep changing the design and remachining parts. So that was kind of the main reason why we chose PLA.
Okay, so anyone who was at the last design review remembered that we talked quite a bit about kinematics. So we're gonna discuss that more because we've done considerably more amount of work on it. So as a recap, last time I played this video that was made to help people actually do animations of dogs, but it was really helpful because it goes over how the dog walks, how its front and back legs are offset from each other. So there's kind of like a phase difference between the cycle of the front and the back leg, and it's by 3/4 of a cycle. And the reason for this is because in the image on the right, it was an animation of the dog walking with that 3/4 cycle delay. And basically how it works is that at all points it keeps this very wide triangle between the 3 points of contact. So the center of mass of the dog is always underneath the 3 feet that are touching the ground. So we want that advantage for our robot. We want it to always be able to support itself and not have to be balancing. So we decided to emulate that and create a front and back that are offset. And then kind of coming from that, we had the idea to create a flexible spine. And this was an additional challenge that we tacked onto the project because we felt like we were capable of working with it. And we hadn't seen it before in any other dog robot. So it is kind of the main thing that makes our dog robot unique from other dog robots. So as I mentioned a little bit before, a flexible spine is a kinematically solvable mechanism because we can know the position that it has to be in at any point based on that 3/4 cycle offset. And then it's a pretty simple calculation to say if the front and back need to be offset from each other at this angle, this is the angle of the two servo motors controlling the flexible spine. That's the angle that they have to be at. So our last design review, we were discussing different ways to make the spine. We set on just using 2 servos. So it's the minimum number of links that you can use to achieve this. And then the servos will actuate the spine to create those correct angles.
So this kind of plays into our discussion with the spine. Is one thing we realized once we started to talk about the spine was the path movement of the dog's feet as it's moving are going to be influenced by that spine movement. So originally we had decided on 8 actuators, so 2 motors in each leg, because it was simpler and it provided all the necessities for walking and turning. But with the spine as influencing the movement, we needed to find a way to have the feet follow a straight path versus this circular curve that you'll see in a minute. But with that decision, we went back from our 8 actuator choice to 12, which at our previous design review, we had decided we were leaning towards 8, but then we had to make the switch back to 12. So then on the next slide, you can kind of see right here on this second image, the sketch, you can see this path that the legs are trying to, the feet are trying to follow because of the curve of the spine. And then there's some more sketches above that too. So as it's moving, since the spine is going to be oscillating back and forth, the legs are not going to be in a straight line the entire time. And so the feet will also be following this curved path. And so in order to facilitate for that, we have to have 3 motors per leg so we can have more manipulation for that path of movement, which is still not a benefit. It's just more intensive coding for that. And also we have to account for that in the design process. But overall, it will give our dog a lot more mobility freedom.
Yeah. So our final design that we went with can be seen in these images. So previously we were going to have 2 motors per leg, which is the theta 3 and theta 4 labeled in that kinematic chain diagram. But in order to do this thing where we have to be stepping outward and then adjusting our sort of the Z angle of the leg as it's moving, we've added that theta 2, which has a axis of rotation perpendicular to the other leg axes. So it expands it was on the previous slide, it expands the workspace of the limb, which is like a robotics concept, from basically the leg was only able to trace out like a cylinder to now it's able to trace out like a whole sphere basically, or a shape that's similar to a sphere that has a 3-dimensional volume. Yeah, so now we have 3 motors in each leg, and then there are 4 legs, 2 of the same kind of servo motor in the spine, and then eventually 1 for the head and tail. So we purchased 16 total servo motors. When we complete the head design, there may be additional smaller servo motors in the head to do things like moving the ears and the jaw. But basically that's the main motors of the robot. It can be run off the 16 motors. Yeah, and then the last image shows it turning. So when it's turning, this additional degree of freedom also helps us because it allows the leg to basically move in a curved path. And that will create, you can imagine that instead of the robot moving on the ground, imagine the robot's held stationary and the ground is moving as if it was like a rotating treadmill. So that's what will allow the robot to move in a curve, is by matching its stride to the curve of that ground as it's walking, if that makes any sense at all. Yeah.
So in terms of the kinematics that we started talking about earlier, we started to perform some analysis on forward and inverse kinematics. So basically we had a couple of extra meetings. The first one was basically just kind of like an informational session. We just kind of reviewed material from that class, MAE 163 to 63A, and just kind of talked about the general concepts of how this kinematics works and how it will be implemented into our robotic system. And we all worked together to find a solution for the kinematics. So basically, the end result is that we're going to be, we have these equations that can move the servos and trace this path in space. So as you can see here in the picture in the middle of the page, this is the DH parameters, which shows the angles and link lengths. This is just basically the parameters that you put in order to get your forward kinematics, and then you're going to use forward. So forward kinematics basically just gives you the end effector position, which in our case is going to be the foot, and that's with respect to a fixed position, which is going to be the kind of midpoint between the shoulders or the hips in our case. So that those forward kinematics gives you the rotation and position of the foot relative to your fixed base frame. So that's kind of what we started here with the forward kinematics. And here are the results. So it's in terms of theta 1, 2, 3, and 4, where our three unknowns are going to be theta 2, 3, and 4, because theta 1 is going to be a constant. So we have, as you can see, the format of the forward kinematics is that the first portion is the end effector rotation matrix, which is just basically describing orientation. And then the last column is the end effector position, which is just a position vector in XYZ with respect to the base frame to the foot of the robot. As you can see in the top right, that's just basically showing the kind of the goal matrix, which is again a 3x3 rotation matrix and then a 1 position vector at the end. And yeah, here we wrote it in shorthand in terms of C3 is just cosine of theta 3, C12 would be cosine of theta 1 plus theta 2. So we just wrote it in a shorthand using trigonomic identities so that it could be in a clean form. And then the next step, which we have started, is to solve these equations for inverse kinematics, which is basically just to get isolate each one of our variables, which is going to be theta 2, theta 3, and theta 4, which correspond to our joint angles that we're going to be inputting into our servos. So we're going to be working on doing that by hand and via MATLAB, and we're going to try to compare the results. So in terms of the leg itself, we did some basic finite element analysis, just static tests on SolidWorks. As you can see on the left is the upper leg, and on the right is the lower leg. The upper leg has the pulley system, and the lower leg is just attached to the bottom leg, where you can see the interface right there. We obviously, it's hard running FEA on 3D printed parts, so we're not really going to. So this analysis is not going to be super useful to us right now, but as you can see, like in this bottom, or in the image on the left, we can see that in these kind of sharp corners, we have high stresses. So that's something that we can just edit the design a little bit and try to take those away. And then on the right as well, we can see at the interface between the kind of sphere where it's going to be the foot of the robot, we can see also high stresses. So we can just use the FEA to kind of drive our design a little bit, just to make some kind of finer touches and a couple more iterations to just make sure that the design is as robust as possible.
Next is the, can you hear me, by the way? All right, cool. Next is the chassis and exterior portion. So here in the two images feature the spine and the hip mobility aspects. So first on the bottom image, you see the base of the spine, which is the center connection, which goes to the hips and shoulders. And that'll feature two servos with a linear servo horn that attaches to the hip and shoulder, allowing it to actuate back and forth. And then on the above image is a photo of the two of the servos, which are going to be used in the leg integration with the chassis. And they will use a circular horn in order to rotate the bottom section, allowing it to move as we would like it to. So from the last design review, we had a design with 3 links, and we tested it, and we found that the durability of PLA should match, or it should work for what we want. And also we reduced it down to only one center link, which is the base, as you can see in the image below. And we believe that that'll give us plenty of mobility for any of the walking movements that we'd like to have. And instead of having a snake-like spine, we'd have just the hips and the shoulder be these T-shaped attachments that attach to the legs. And given the increase to 12 servos, this gives us the mobility that we need, where the 3-link design would have been necessary if we only had the 8. And the pros of this is that it's a simpler motion, and it's a lot easier to identify because there's less servos in the link, the spine to keep track of. And the cons is there's less range, but we don't think that we'll need quite as much range for the actual dog. So this is the exterior. The above portion is a prototype that we have. And essentially the exterior is gonna be like a armadillo shell that bends with the movement of the spine and other aspects of the robot. They'll be later changed due to like the dimensions of the robot as those change. But essentially the goal is to make it have a surface that protects all the electronics and such, but also moves with the robot. Yeah. And next will be Sardor, who will go over the ear design.
Yeah, so we started thinking of how the ear would work as well as part of the exterior. And we thought that, well, we were inspired by the mechanisms of how a finger works, of how it is able to bend and contract and then extend backwards. And we thought we can actuate that with a single servo and a set of non-elastic and elastic strings. So in this case, as you can see in the photo on the right, that is our, well, prototype that we thought of. The elastic string aspect of it would be running from the attachment that you can see at the point on the top third to the hole on the inside, and attaches on the bottom third. In its neutral and resting position, it will be equivalent to the image to the left. So the top third will be flapped down. And then the servo motor, when actuated, will pull the string so that the two top thirds are aligned linearly, but only the bottom joint bends down. So it's gonna be more equivalent of the dog, well, bending its ears up and down. And yeah, we can do that either with a single servo for both ears, or if we want them to move simultaneously, or we can have individual servos for each ear to have them, well, actuated also individually.
All right, hey guys, I'm Rohan. I'm one of the CS leads, and I'll give a bit of a recap first on what we did before, if you weren't at the last design review. So one big thing was deciding between ROS and like a custom robot code. And as you can see here, like ROS was just it was like not exactly what we needed for our robot, because we had many parts, or we planned to have many parts like the spine that couldn't be modeled well. And better things about are actually making a custom robot code is that it helps us all get experience in actually doing this, which is a big part of what we do next one. And also it's more flexible, as again, like what I said. And the main like difficulty with making a custom robot code was that we're not really sure how to make a quadrupedal motion. And we still have yet to get to that. And that'll be a challenge for us to achieve next quarter, hopefully. So in this quarter and winter quarter, we fleshed out more of the ideas that we decided upon. And some of the ones you mentioned last in fall were listening to commands, reacting and being pet, indicating your mood, moving around to designated locations, and even using computer vision to detect like things like a ball and maybe turn towards it or walk towards it, and using a light sensor for sleep cycles. But Ethan will now give you a more fleshed out idea of what we have decided to settle with.
Yeah, so
You want to share the
yeah,
portrait?
I'll share. So this quarter we really flushed out the kind of behaviors that we wanted to. Wait, you need
Yeah,
a
sorry, I
name.
realized. There you go.
So this quarter we really, can you see?
Yeah.
Okay. This quarter we really flushed out the kind of behaviors we wanted the robot to do, and so we created a flowchart to kind of put it down on paper what exactly we wanted the robot to do. So I'm gonna go through a little overview of how it works. So obviously you need power on the robot, and we're gonna have the process boot up. And in terms of the exact details of what is going to happen in each process, that's still to be worked out. But the point of the flow chart right now is just to get the processes down and figure out like a general overview. So first you need to boot up, and this could be some kind of like system check or just waiting for everything to turn on and not throw any errors. And then it immediately goes to an idle process. And this is just the dog waiting for some kind of input, whether it's touch, voice, or no user input. And so the first thing we're going to do is if the dog doesn't get any user input for 30 seconds, it's going to immediately go to this wandering process. And this wandering process is probably going to be a predetermined route that the dog would take. And it's just going to say like do a circle around a certain area and just wait for user input. And if it doesn't get any user input for 5 minutes, it's going to shut down because we don't want it to be powered on forever, and so it's going to shut down, and that's a pretty simple process. But if it does get some kind of user input, then it's going to go back to the idle process, and then it's going to determine what kind of input it received. So first we're going to go through touch. So our touch sensors, we're going to have 3 different touch sensors on the back of the robot, like on the spine, and depending on what kind of like which sensors received input will determine how the dog will react. So the first is the default pet, and the default pet is if the dog receives input from 2 or less touch sensors, and it's going to do some kind of default pet that's kind of like a pat, but not exactly a pet. And so if we get 3 inputs from the touch sensor, so all 3 of them get some kind of reading, depending on the direction of the pet will determine whether it's a good pet or a bad pet. And so it'll react accordingly depending on what kind of pet it gets. And then that loops back to the idle process. And if it gets voice detection, it'll go to the voice detection process. And depending on what kind of input it gets, so we have shutdown, unintelligible, so some kind of voice input that it didn't recognize, or something like do a trick, sit, wagtail. And so specifically with the tricks, we have 3 different processes. So we have turn, wagtail, and sit down. Those are pretty simple, and they do exactly what it says. And then we also have confuse, and that's for the unintelligible voice command. And these all loop back to the idle as well. And then with ball, that'll be for object detection. And so our current plan, although it's still rough, is that we're going to have the dog detect the object and find it. And we're going to say the object was a ball. It's going to retrieve it and then return it back to the human. And then after that, it's going to return back to the idle process. And yep, that is it.
Awesome, thanks. Return to the slideshow. All right, yeah, we went over this.
Okay, so can you hear me? In order to work on the Raspberry Pi, we finally were able to meet in person this quarter. So we were able to set up our Raspberry Pi. And since we only meet around once a week, we wanted to get the Raspberry Pi running up in the lab without having to visit the lab every time we needed to write code or send code to it. So we set up a server on the Raspberry Pi, and that's running in, I think it's running in the lab right now. To get around the UCLA Wi-Fi blocks, which blocks peer-to-peer connections on the network, we had to use a workaround, and we used a program called Hamachi to set up like redirected IP address that we could SSH to. In order to have a GUI to look at, we can also use TypeVNC, and we could launch that via the SSH path. And yeah, so now we're able to get scripts onto the Raspberry Pi remotely. And as for the speech recognition, as we mentioned earlier with Ethan and the flowchart, there are a few things that we can say to the dog and it'll do various things. So we got the Python code for that running. We still have to finalize which keywords can be used, maybe create a list somewhere and for future reference. And we also have to test it with the actual hardware of the Boelt dog, which we don't have yet, but once that comes around, that's something on the to-do list.
So as Ethan already mentioned, we are planning to have touch sensors located on dog's back. We'll have at least 3 sensors to be accurately determine the direction of petting, and the behavior will depend on if you're petting along fur or against fur. So for now, we already came up with a Python code for 3 sensors, and we tested our code for 1 sensor. So currently we're planning to test the program for all 3 sensors, and also calibrate it based on, for example, how fast we are petting the dog. So as I mentioned a bit earlier, we're doing some work with the computer vision so we can hopefully detect some objects, some common objects, like maybe a tennis ball that the dog might see that a person's holding, or maybe identify a person, and use that to either guide the dog's behavior, as in walking towards a person, or if we get sufficient enough recognition software to avoid obstacles. So on the top right, you can see like kind of like a preliminary, just like testing, I guess proof of concept kind of thing, with filtering out for the color blue, and that right there is I guess the old version of the spine we held up, and it looks pretty clear. There's no erosion filters or anything to remove the small bits, but it still gets the main picture of getting the actual spine. And on the bottom, again, I didn't really do any erosion, so I think it detected my face or something, but it filtered out this UCLA water bottle and drew a bounding box around it. And with that, we have XY coordinates, and we can drive towards, drive the robot towards or away, I guess, from those specific coordinates. I guess that would be in its field of view. So this is implemented using OpenCV. It's a package we can use in Python, and it does a lot of this for us, like filtering based on these hue saturation values or drawing a bounding box. And future developments, as you can see on the bottom left, is using more complex object recognition using machine learning. This is one, I guess you call it a package called MediaPipe. It has a lot of common objects, I believe. Like you can see it detects the bananas, the bottles, and the cup with good accuracy, and it draws bounding boxes. And even if the objects are close together, it still detects them pretty well. So we'll see how far we can get with OpenCV, and if machine learning provides a better accuracy, we might take that route to guide our computer vision.
Yeah, so just to summarize, first of all, thank you everyone from the Boelt team. That was a great overview, and really, was sort of an insight into the design process as well. And it's really cool to see the results of all that thinking. I know that X1 is primarily a conceptualized basing project, but it's great to see that you guys really start to put these things into real action. So yeah, so just to get to the next steps, again, we're going to look at things along the 3 lines here in regards to legs, chassis, and CS. So yeah, there's going to be remaking the leg CAD design as well. Or maybe also just cleaning up the grab CAD as well. We're going to add mounting points, fasteners according to best practices. And then we're going to eventually solve the inverse kinematics, not only of the legs, but also of the oscillating spine, which itself might not be an inverse kinematics problem, per se, but rather also a mobility problem. Chassis and exterior, same thing, best practices in fastening, and also working with these armor plates, which we started developing a few weeks ago. Did something to just, cover the spine for aesthetic purposes and also for mounting touch sensors. And for CS, again, it's just fleshing out all the work that's been done so far, writing the code based on what chassis and exterior are doing. I think the kinematics code is going to be written in, I believe, MATLAB. It's going to be solved in MATLAB. I think it might be written in Python, but that's to be determined. But yeah, there's also electronics work as well. Looking at the power considerations, power draw, regulating voltage, all these things that will eventually pop up as we get further into the project. Then there's also the behavior. We have to actually implement that as well in code. And these are all things that I think that if we take a look at block by block, we're going to be able to make good progress on next year.
Yeah, we'll
Right.
open it up to questions. I can go back through to any of the sections that we covered. Yeah, anything, any comments, feedback of all kinds. Or we've made a perfect robot on the first try.
I was about
That
to
could also
say,
be an
there's
option.
nothing wrong with it.
There's nothing wrong.
Prove us wrong.
Yeah, obviously a lot of the designs are in a preliminary stage, and have current issues that are being worked on. But yeah, any questions?
I must say, sorry not to interrupt the silence, but if you do, this is both members and alumni as well. If you have any questions that may pop up, simply look at the next slide we're going to show you guys, and just feel free to send us a message or any comments after the meeting as well, if anything just comes into your head while digesting all this information. So,
Yeah, for sure.
but yeah, of course, the floor is open for you.
Yeah, our last slide is just some contact info for ASME and the X1 email. Our leads next year will be Avi and Daniel, so you can now reach them through the X1 email.
Mhm.
All right. Yeah, you guys are free to head out. Great job to everyone who presented today. It was awesome. And yeah, we'll keep an eye out for messages. People send us messages afterwards.
Absolutely. Thank you so much, guys. Great having you all in attendance as well. So great work.
Really good designs here, guys. Nice to see some good progress.
Well, thank you.
And thank you so much.
I see the alumni lurking around, but they're not saying anything. No critiques, y'all. I guess not.
Nah, y'all are killing it.
All right. Thanks,
Seriously.
John.
Yeah. Sorry, I like changed my mic input. I always do that with like Zoom meetings just in case I accidentally unmute. Forgot to put it back.
Oh no.
Yeah. No, it looks cool. A lot of good
Awesome.
math work too, which is nice to see.
Putting that class to work.
Yep.
Yeah, it's just ripped straight out of Hong's slides, basically.
Have you showed him the work you guys are doing? He'd like get a kick out of it. I mean, if he even sees the email. I know man is stupid busy.
Yeah, I know. I mean, I invited him to this, but of course he's not
Fair.
coming. I didn't talk to him about this project because a lot of this work we did really recently. I showed him Brewbot at one point. He was like, "Oh, he looks so friendly," but yeah, I know he might be interested in it.
At the very least, you could just shoot him an email and be like, "Hey, here's the math that you taught us. Thanks. Bye."
Yeah. Yeah, I feel like
Yeah,
I feel like a lot more X1 students might want to take that class now because they seemed really interested in the kinematics stuff when we were presenting it.
Mm-hmm.
Yeah, it's really
It is
cool
very
math.
much like an information chain,
Mm.
because I get it from Rebecca. I have to say to some people who may not have made the lead. So like there's like a degeneration of information, along this chain. So like definitely, for all those that are still in here, take the class if it so interests you. So we do need that
Yes.
refresher. That that firsthand information.
I did feel gratified though because I did my like 1 hour spiel about how forward and inverse kinematics works, and then one of the students was like, "So how do they make a whole class out of this? It seems so straightforward." And I'm like, "Wow, I just taught it better than Hong taught it in a whole quarter. Amazing." No.
Or Hong taught it so well that you could teach it in an hour.
Exactly. Yeah.
You'll never know.
Yeah, it could have been. All right.
Alrighty, I'm gonna hop off. See you guys.
Yeah, thanks for coming by.
Mm-hmm.
All right. Thanks, John. All right, good. Very cool.
Hayato sends a
All right.
thumbs up.
Hayato's reacting
Very good.
positively here. So just gave us a thumbs up.
Nice, nice.
All right. Wish I could react to your reaction, but that's like too many reactions.
Oh, I forgot to stop recording. Oops. Oh, this is in the video now.